Good evening again. Exploring the Solar System Part 2. How we explore the Solar System with spacecraft. So we can ask the question, well, how do we actually get there if we want to go and see what planets are out there? What do we do when we get there? How do we get images back? Well, we send spacecraft out to get more than just images. We want to get all sorts of data, but images are what a lot of people are interested in. So how do we get images back from spacecraft that we send to planets in the solar system? And again, I'll ask the question, what next? I thought I would start by saying, well, how many spacecraft have we actually sent out? How many spacecraft have left Earth and are looking at either the moon or the planets or asteroids or any aspects of the solar system? I started counting them up and then realized I really didn't have enough fingers. And then I realized the list was much longer than I first thought. I know you can't read all of that, but this is all of the spacecraft that have been sent out into the solar system. From the very early ones to the latest ones. I'm not sure if this needs an update, but Europa Clipper in the bottom right is the latest one that I can think of. Hundreds upon hundreds of spacecraft have been sent out to get various aspects of data back from various objects in the solar system. If we think about what we were talking about in the last talk, getting to Mars, if we think about the way the Earth goes around the Sun, Mars is in an orbit outside the Earth's orbit, and you might think that in order to get from Earth to Mars, we perhaps wait until Earth and Mars are as close as they can be in their orbits, and then we go as quickly as possible from Earth to Mars. But actually, the most efficient way of getting from Earth to Mars is to leave Earth when it's on one side of the Sun and arrive at Mars when it's on the other side of the Sun. It seems a little bit counterintuitive because that seems like it's got to be the longest way to get there. Well, arguably it is the longest, but it actually needs the least amount of fuel. So the actual orbit that you fly to go from Earth to Mars is that elliptical orbit. The closest to the Sun is equivalent to the Earth-Sun distance, and the largest distance in that elliptical orbit is equivalent to the Mars-Sun distance. And that needs a little bit of a kick when you leave the Earth and a little bit of a kick from a rocket when you arrive at Mars, but it actually uses the least amount of fuel, which means you can take a much larger payload or more scientific equipment, or a larger rover can be sent to the planet. Well, okay, that's how you get to Mars, but what about planets beyond Mars, Jupiter, Saturn, etc.? Well, back in the 1960s, it was realized there's actually quite a neat trick you can do. If you leave Earth, as you pass a big planet like Jupiter, you can use a so-called gravity assist, a slingshot if you prefer, that actually sends you even faster out into the outer solar system. So this idea was planned in the 1960s, and then it was used in the 1970s for the Pioneer space probes and the Voyager space probes. Let me just run that simulation one more time. You leave Earth, and then as you pass Jupiter, you use its gravity to slingshot you. Notice the change there, the dog leg. You're going much faster, and you're heading off in, if you calculate it correctly, the right direction to send you on to another planet. That was done for Voyager 1 to visit Jupiter and Saturn, and then for Voyager 2 they took it one stage further. They left Earth, they had a slingshot as they went past Jupiter that sent them on to Saturn, and then they did the same again. They had another slingshot as they went past Saturn, which sent them on towards Uranus, and then yet another slingshot to send them on towards Neptune. So that means that the spacecraft was going much faster than it would otherwise without this idea of a slingshot past a planet, which means you get there faster. Well, it still takes years, but you can cut the journey time by perhaps a factor of 2 or so. And because you're not using a rocket to go faster, you're using the gravity of another planet. That means you use less fuel, and again, less fuel means you can have a bigger payload, a bigger spacecraft, more scientific equipment, more cameras. So it's always a good thing to save as much fuel as possible. So this idea of exploring the outer solar system by using the gravity of some of the planets you're visiting was a great idea and has been employed many, many times in the last few decades. Here's one of the earliest images we've taken of a celestial body. Not sure if you can figure out which particular body this is. But if I tell you that it was taken from the spacecraft Luna 3, that gives the game away. This is the moon. It's not the familiar near side of the moon, which is always facing the Earth. This is the far side of the moon. And we can't ever see the far side unless we have a spacecraft that goes round to the far side and takes an image. This was 1959. We can clean up the noise a little bit, but you can still see it's a rather low resolution image compared to what we're used to these days. But when you remember that this is the 1950s, this is before the technology of mobile phones having cameras built into them, before the technology of any digital camera, how did they get an image from 1959? Well, this was actually taken by exposing film, yes, normal film, emulsions, and they were exposed and then put into a little chemistry laboratory which developed the film and then fixed the film and then dried the film. And then a little spot was scanned over the film, much like an old TV screen, a cathode ray tube, and the amount of light that came through the film was then detected by a little photo detector, and the signal from that photodetector was then transmitted to Earth, and there the image was reconstructed, much like a fax machine takes an electronic signal and uses it to generate an image. That's how the image was generated in the 1950s. When we compare it with a much more recent image, for instance 50 years later, this image was taken by an orbiter, a NASA orbiter, and you can see that although the NASA orbiter is much higher resolution because it's modern technology, notice that the original image from the 1950s basically got it right. It had the dark blobs in the right place, it had the bright blobs in the right place. It didn't tell us exactly what these objects were. Are these mountains? Are they craters? Are they seas? But it did tell us that the far side of the moon looks different to the near side of the moon. It was realised that we don't want to use film forever because it's a real pain having to develop it and then scan it and then send the signal back. So in the mid-60s, the Mariner spacecraft were the first to employ digital cameras. In fact, these were the first digital cameras ever. You basically owe the digital technology that's in your mobile phone to spacecraft. Spacecraft have driven technology, and the desire to have digital cameras that can take pictures and send back to Earth ultimately have given rise to digital cameras which now are in everybody's phone or iPad or whatever. When this spacecraft flew past Mars, the camera stored its images on tape. It wasn't possible to send back the images in real time because the rate at which you can send information by radio is limited. So the camera stored all of its images on tape, and once it had flown past Mars, it then replayed the tape somewhat more slowly and then sent the information back to Earth, where they could then generate those images. Again, we can take that image and clean it up a little bit, and we can clearly see features on the surface of Mars, craters, etc. So this was from the mid-60s, July 1965 for this particular image. We've now effectively visited every major body in the solar system. All the planets have been visited by spacecraft, some of the dwarf planets, a number of asteroids and other objects have been visited. I can't talk about all of these things, so let me just pick out a couple of missions just to give you an idea of how it works. The Cassini mission explored Saturn and its rings and its moons for quite a while, for 13 or so years, between 2004 until 2017. There's some numbers on the left-hand side, which I can let you read if you're interested. Millions of commands were sent to the spacecraft. The spacecraft travelled billions of miles or billions of kilometres. Huge amounts of data were acquired and sent back to Earth. You can see the size of the Cassini spacecraft in the bottom right here. There's a standard person to give you an idea. You can see that the Cassini spacecraft is not particularly small. It's about the size of a house, basically. Why did it crash into Saturn in 2017? Once it had fulfilled its mission, why didn't they just leave it orbiting Saturn and just let it die? Well, there's the outside chance that maybe one of the moons of Saturn might harbour life, much like the moons of Jupiter might harbour life. And what they didn't want to do is leave the Cassini spacecraft going around Saturn with the possibility that one day, centuries from now, it might crash into one of those moons and potentially contaminate the moons. So they deliberately crashed it into Saturn, where we believe there's no chance of life having evolved, and so that keeps everything nice and clean. From Earth, or at least from low Earth orbit, the Hubble Space Telescope is able to give us some quite nice views of Saturn. But when we get close to Saturn with the Cassini mission, we can get much more detail. So for instance, if we were to have a look at the ring system, we can see much more structure within the rings. The rings are not a solid object, they are trillions of small icy particles that are all independently orbiting around the planet. The more we look, the more detail we see, and it's amazing how much it looks like a long playing record. For those of you who remember long playing records, when we look in detail, we see so much structure, and understanding the dynamics of why these particles have this structure and how they're affected by the various moons that are orbiting Saturn is part of the mission. The ring system is incredibly thin in the sense that it is huge, 250,000 kilometers in diameter, but only perhaps a few meters or perhaps tens of meters thick, so incredibly thin. If we catch it at the right time, when the sun is coming in at a very shallow angle, we see that part of the ring system actually casts shadows on the rest of the ring system. So it looks like, although most of the ring system is very flat, some parts of it appear to be rather buckled and rather rough. And again, understanding the dynamics of why these bumps exist, why they exist at particular distance from Saturn and how they're related to how the moons are going around Saturn, that's part of what this mission is doing, trying to understand the dynamics of Saturn and its ring system and its moon system. This is something that you can't see from Earth. The Cassini spacecraft was commanded to go into Saturn's shadow, and here we're seeing Saturn lit from behind. So the sun is directly behind Saturn, shining through the rings from behind and also through the atmosphere. We can't get this perspective because from Earth the sun is always close to the Earth, and so we always see Saturn sunlit. But here we see it from behind, sunlit from behind. And scientists are very interested in this because if you look at how the ring system reflects light from behind, it tells you about how large the particles are that are reflecting or scattering sunlight. So we get a very interesting set of information about just how large these particles are, what their size distribution is. Saturn has a moon called Titan, which has a very thick atmosphere which stops us seeing what the surface of Titan looks like. And so this mission, as well as Cassini taking images of Saturn, also had a small spacecraft bolted onto the side, and that was released and then parachuted into the atmosphere of Titan. And as it was parachuted into the atmosphere, it took this video. So prior to this, we did not know what the surface of Titan looked like. But as it enters the atmosphere, the video shows us that this moon far from being like our moon and completely lifeless, it appears to be a very interesting world in its own right. It has mountains, it has rivers, it has lakes, it has clouds, it has rain, much like Manchester basically. Well, it's probably not water because it's so far from the sun, it's probably more likely to be methane. But this is a very dramatic world in its own right and definitely worthy of more study. It is not a lifeless rock in the sense of completely barren like our moon appears to be. Here's another mission, this one going to Jupiter. It arrived in 2016 and it's still there. As you can see from the picture on the left, this is a mission which has solar panels. It was considered the cheapest way of having this mission work. The solar panels need to be quite large because at this distance from the sun, the solar panels are not picking up that much sunlight, so it needed rather large solar panels. And basically at any greater distance, solar panels are very ineffective. But this was considered the best way to have a Jupiter mission. Again, some numbers there. Enormous distances travelled, huge amounts of information sent to the probe saying, look at this part of Jupiter, look at this moon, take an image, take a video. And again, thousands of images taken and millions of commands sent from Earth telling it essentially what to do. Let's have a quick look at Jupiter. There's an idea of what Jupiter looks like. Let's unwrap it so we get an idea of these bands that we see, these bands that seem to run through the equator. These bands seem to dissipate at the poles, but very clear bands and zones. Different colours, we think that's because we're looking at different compounds and different elements, perhaps at different altitudes within the cloud system of Jupiter. We think some of these brown and salmony colours, we think that's probably the result of methane and ammonia mixing with other elements like perhaps sulphur and phosphorus. And we also realise that there are storm systems raging. For instance, here we see a storm system that was seen hundreds of years ago and appears still to be raging. Why is it that storm systems on the Earth seem to come and go and dissipate after a few days, but a storm system on Jupiter can last for hundreds of years? Studying the weather system and the clouds on Jupiter might help us get an idea of how weather systems operate. Juno spends a lot of its time away from Jupiter and then plunges in and skims over the cloud tops. Here we see a time-lapse video of it plunging over the surface. The occasional flashes of white you see there are lightning storms in the upper reaches of the atmosphere. You can see there's an enormous amount of detail in these storm systems. The way the very rapidly rotating storm systems, the rapidly rotating winds have whipped up these structures is very interesting to meteorologists who are trying to understand, for instance, these storm systems like these white dots here. We're now looking more at the polar regions, which is a bit of a blue colour. Let me just take a still from that to give you a better idea. Here the colours have been somewhat enhanced, but yes, Jupiter is mainly a sort of orangey pinky colour, but it does appear to be much more blue towards the poles. And again, understanding these colour differences on the planet will help us understand the makeup of Jupiter and why its clouds behave the way they do. A nice image of a particular part of that cloud system. It really does bear striking resemblance to a watercolour that's been left out into the rain. We're not altogether sure what this object is at the centre. It appears to be rather dark. It's thought that maybe this is a vortex and maybe we're looking down into lower levels of the Jupiter cloud system. This image was taken from a height of only a few tens or 15 or so thousand kilometres above the cloud tops. When you remember that Jupiter is some 10 times bigger than the Earth, this is effectively skimming over the cloud tops. We should remember that the solar system is not just the Sun and 8 planets and perhaps a few dwarf planets as well. New Horizons was sent out to explore Pluto, a relatively recently demoted planet, which is now called a dwarf planet because of its effectively because of its size. New Horizons was sent out into the outer solar system, again because it's so far from the Sun it can't use solar panels, so just like Mars rovers, some Mars rovers, it has a thermoelectric generator on the back end here to provide it with power, hopefully for decades to come. And it's now gone beyond Pluto and is on its way out of our solar system. As it flies out of our solar system, it's flying through a region where there's lots of tiny icy bodies called the Kuiper Belt, and it's intended to go and have a closer look at some of those bodies. They're still a long way apart and it can't really afford to steer. It hasn't got enough fuel to go looking for particular things, but hopefully its trajectory will take it past some of these objects and it will take a closer look at these objects beyond Pluto as it leaves the solar system. And in addition, there are something like 300 or more moons. Most of these moons are around Jupiter and Saturn. They take the lion's share. There's a smaller number of moons elsewhere in the solar system. That's what some of them look like. Some of them, the larger ones, are relatively spherical. There's Titan with its rather hazy atmosphere that stops us looking at the surface directly, hence the idea of sending Huygens in, parachuting it in to look at the surface. Some of the smaller moons look really weird, like this sort of walnut-shaped one. Some of them are small enough that they don't form spheres, they look more like little potatoes. And some of them, well, there's our moon there, our familiar moon with the face that always faces us. And some of these moons look more like the Death Star than they do moons. This one apparently was hit by a big object which produced this huge crater. If it was any bigger, it probably would have broken the moon apart. But if we look at some of the largest moons, again, these all look relatively spherical because the large moons tend to be spherical because of gravity. There's the rather hazy atmosphere of Titan. There's our own moon again, all of these to scale. But of particular interest are these moons of Jupiter, the 4 biggest moons of Jupiter, Io, Europa, Ganymede and Callisto. The closest to Jupiter is Io, looking a little bit like a pizza. This is close enough to Jupiter that it's being stretched and distorted by Jupiter's gravity, and that produces a lot of volcanic activity. So that's why this one is so active. But in fact, a lot of the interest really goes to the other 3 moons, Europa, Ganymede and Callisto, the so-called ice moons of Jupiter. These are all covered in ice. And that might seem very boring, aren't they? Just basically lumps of ice, spherical lumps of ice in space. Well, no, because although they have a surface of ice, we have reason to believe that under the ice there is a liquid ocean. Somehow there is liquid water. Something is keeping this ice from freezing throughout the body of these moons, and there is liquid water. So if there's a heat source keeping the water liquid, and there's water itself and probably a whole load of different compounds that are required for life to evolve on Earth, all of the ingredients seem to be there as well. We think life formed in Earth's oceans, and it's possible that the conditions were right, the existence of liquid water, a heat source, and various elements, not just hydrogen and oxygen in the water, but heavier elements as well, perhaps other elements like sulfur and phosphorus, carbon, for instance. Maybe it's possible that life has started in these environments, which is why there's so much interest in the ice moons of Jupiter and indeed Saturn. And relatively recently, 2 missions have been sent to explore the ice moons of Jupiter. The Europeans have sent the JUICE mission, Jupiter's icy moons, and NASA have sent Europa Clipper, which is going to take a much closer look at Europa and probably other moons as well. So those were launched relatively recently, the last year or so, and they're on their way and will be arriving in Jupiter in a few years' time. And then they will be taking data which hopefully will give us more information about these subsurface oceans. I said something about getting information back from these spacecraft. Up till now, for the last 50, 60, 70 years, we've done that by sending radio waves back from the spacecraft. So generally speaking, for spacecraft that are going a long way from Earth, they need a big radio dish which sends the radio signals back to Earth, and then a really big radio dish on Earth picks up those very weak signals and hopefully picks up the transmissions and the data and reconverts those back into scientific information and images. But just like the idea that, well, a number of us have got broadband connections which are connected by fibre optics, in which lasers are sent down the fibre optics because lasers can carry much more information than radio waves. So rather than sending radio signals, why don't we send laser signals back from these distant objects? In principle, a laser, even a relatively modest power laser, can produce faster transmission, not in the sense of the length of time it takes to get the data back. Lasers will send the information at the rate of the speed of light, just like radio signals, but the amount of data you can send in 1 second is much higher on a laser beam than it is on a radio beam, just because the frequency is much higher. And generally speaking, a laser will use a little less power. So instead of picking up the signal with a radio dish, you could pick up the signal with a large telescope, such as indicated here, the 5-meter Hale telescope in California. And this test has been done. A spacecraft that was sent out into the asteroid belt was undergoing radio communication back to Earth, but as a test, it also sent a laser signal back to Earth. What would they use as a test? Well, there's no point in just sending an image. That's only a tiny amount of data. They decided to send a high-definition video on a laser beam. What video would you send? Well, the people at NASA send, well, it doesn't really matter what the video is. So if we're sending a video on a laser beam, let's send a video of a cat chasing a laser beam. So that's what they did. They made a high definition video, sent it on the spacecraft, and then the spacecraft transmitted it back on a laser beam. When the spacecraft was 50 million kilometers from Earth, they got a data rate of 260 megabits per second. That's faster than some people can get in their broadband connection from a server that's 10 miles down the road. And this is at a distance of 50 million kilometers. Even when the spacecraft was at the asteroid belt at a distance of 400 million kilometers from Earth, they still achieved data rates of 8 megabits per second, much faster than they could achieve with a radio transmission. So we still always will have a time lag between when the data is sent and when it's received, but it now means if we want to use lasers, we can get much more data back per second, per minute, per hour, compared to having to transmit for days and days and days, or weeks or months, in order to get the transmission down via a radio beam. So that, it looks like, is where the future is heading. So just to recap, there are various missions around at the moment. Bepi Colombo is a mission that is going to Mercury and will go into orbit very soon. I've said that Cassini was sent to Saturn and has now crashed into Saturn, so that is no more. New Horizons is on its way out of the solar system. Juno is still in orbit around Jupiter. And relatively recently, we've got these 2 new missions to explore the ice moons of Jupiter, the JUICE mission from the Europeans and Europa Clipper from NASA. So I'll make a handout available to you so you don't have to jot down these particular web addresses. But if you want to know more about missions that are currently active and missions that will be sending back data in years to come, these various web addresses will tell you lots about what's going on, why they are visiting these planets, what they hope to learn, and what we expect to get in years to come. Thank you very much.